All right, welcome in everyone. My cat is guarding me. He's asleep at my feet and probably will stay that way. So let's start here. Uh, in this one, we have some matching to do relevant to chapter 27. And so we have to take a look. Hmm. Sorry, I have to turn off chat for a moment. Otherwise, we can't see this page. So here's the structures we're given. And I would expect all of these to be structures that you could identify from chapter 27. The first one it asks about is a soap. In class, we said that a soap is the conjugate base of a fatty acid. It's essentially what you get after hydrolyzing a triglyceride, and you get glycerin and three fatty acid carboxylate molecules. So you're looking for a fatty acid, except instead of COOH, it's COO minus, and that's compound C. That would be a soap. The potassium salts tend to be solid soaps. Sorry, the sodium salts tend to be solid soaps. The potassium salts tend to be liquid soaps. So the soap is C in this case. Then it asks for a steroid hormone. And in class, we said that steroid hormones, cortisone, cholesterol, bile salts, all of these compounds have the same tetracyclic ring structure, which involve three six-membered rings and a five-membered ring fused exactly like that. And I, of course, don't care if you memorize any particular ones. The one that, if you're going on to biochemistry, the one that might be the most useful for you to almost memorize is cholesterol, because you'll see that one so often. This one's not cholesterol. I don't have cholesterol memorized, but I notice there's a ketone, not an alcohol. So I know it's not cholesterol. In any case, the big question is whether this is a steroid hormone or a bile salt. And remember in class, we said that you know it's a bile salt if you see a cis ring fusion between the A and B rings. And we don't. This carbon on the bottom of the fusion between the A and B rings is sp2 hybridized, so there is no cis and trans. And in order for it to be a bile salt, that would have to be a cis ring fusion. So that one is a steroid hormone. So we'll put A for that one. Prostaglandins, we said in class, look kind of like fatty acids, except they always have a five-membered ring fused in the middle. And this five-membered ring may vary in terms of what's attached to it. But this is a typical prostaglandin. I certainly don't know which one, and I wouldn't expect you to either, but I would expect you to recognize that as a prostaglandin. And then how do you recognize a water-soluble vitamin? Well, a water-soluble vitamin is something that's not in any of the other categories that we mentioned in chapter 27. So it's not a fatty acid, it's not a wax, it's not a soap, it's not a triglyceride, it's not a phosphatidate or phospholipid, it's not what? Terpene, it's not a prostaglandin. It's not a steroid hormone. I'm probably forgetting a few of them, but it doesn't fall into any of those other categories. And it's water soluble. What makes a molecule water soluble? Well, if it has a lot of functional groups on it that either are polar or can hydrogen bond with water. And we have a good candidate for that over here. We've got 208 with 3OH groups. We've got a pyridine nitrogen, which is very polar, and we've got a polar aldehyde functional group. So this is the one that's going to be a water-soluble vitamin. I believe it's one of the B vitamins. If you look up the structure of vitamin C, you'll see another example of a water-soluble vitamin. And if you compare that to the structure of a fat-soluble vitamin like vitamin A, you'll see there's a big difference. So the water-soluble vitamin is F. And we didn't get to use H. There was an example of all of these on that page. So yeah, that's pretty much it for that one. Just matching. Let me put chat back on.
So, Dr. Wass,
Yes.
so for the number 4, it's water soluble because all of those 4 things that you pointed to can bond with hydrogen, can do hydrogen
Well,
bonding.
the OH groups can hydrogen bond with water, and the nitrogen is polar, and the aldehyde group is polar.
Okay.
I guess the nitrogen can form hydrogen bonds, can accept hydrogen bonds. So can the oxygen and the aldehyde. So
Okay.
that's what makes it water soluble. It's quite polar and has several functional groups that can hydrogen bond with water.
Okay.
And to identify a soap is going to be a molecule that's a long chain fatty acid. So it's a long chain carboxylic acid that is the conjugate base of the carboxylic acid. So instead of OH, it's O minus. This is not a soap, that's a fatty acid. This is a soap because it's the conjugate base of a fatty acid. Let me show you something else that's not a soap. That's G. And that should also be one that you should recognize. Should I give it away? I guess I'll give it away. This is a wax. In class, we said that a wax is an ester, and I expect you to recognize an ester functional group when you see it. But it's an ester of a long chain alcohol, which this certainly is, with a long chain fatty acid, which that certainly is. Other questions on that one? This exam's from 2020. This was in the middle of the term. We had to go to online exams and everything. So this was a nightmare. The next question asks to draw a triglyceride. And a triglyceride, as we said in class, is a triester of glycerol, which is 1,2,3 propane triol, with 3 molecules of a fatty acid. So in order to answer this question, you needed to know what glycerol was, and you needed to know what an ester functional group is. And we had some practice in class drawing triglycerides. So first of all, let's get glycerol out here. Glycerol is 1,2,3 propane triol. So that's the structure of glycerol. You will need to know that. And then on all 3 OH groups, we're going to make an ester functional group. And so you need to know what an ester functional group is. We're going to make an ester of the OH group with one of these fatty acid molecules. So the alcohol OH goes where the OH of the carboxylic acid is. And so you go from the oxygen to the carbonyl, and then comes that alkyl group. So that's one ester. And what that means, I expect you all to know what that means too. CH2 in parentheses followed by 16 means CH2, 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 CH2 16 times, followed by CH3. It gets a little bit, it's nice to draw line angle drawings, but when there are that many CH2s, it really gets very tedious to draw all those CH2s and be sure you're getting the number right. So this is a little bit easier way to do it. And then we'll place another ester on this oxygen. oxygen, then C double bond O, then the alkyl group. And then last but not least, we'll do the same on this oxygen. Wait a minute. So C double bond O. See if I can make this do this. I can never remember if I need flush right or flush left. Yes, there we go. So there's your triglyceride. It's a triester of glycerol, which is 1,2,3-propane triol with 3 fatty acid molecules. I'm going to say, do not memorize this structure. This structure will not be the answer to any question on your exam. If I ask you to draw a triglyceride on the exam, it will be a different one. So do not memorize this structure. It's a waste of your time. Other than that, that's basically how you do it. Make sense? Questions on that one? You don't get a trial one. This is something that we had to do during that awful semester when we had to switch from in-person to online classes in the middle of the semester. So this is irrelevant to you guys. That has nothing to do with you. Oops, that's not the right one.
Hold on. I'm pretty sure these are the exact things.
So let's focus on each of these in turn. This is asking you to take this compound and treat it with sodium hydride and THF. This is one of the bases that we talked about yesterday. Oh, I'm getting ahead of myself. First, we have to draw the enol form. Then we'll treat it with sodium hydride. To make the enol form, I can essentially do it with 2 mouse clicks. There's your enol. You change C double bond O to C single bond OH, and you put a double bond right next to it. You should get a structure that's an isomer of the keto form. So this is the keto form, and this is the enol form. The question doesn't say to write that. I'm just doing that for teaching purposes. So that's how you write the enol. Then the question says to treat this aldehyde with sodium hydride and THF. And you need to know that NaH is H minus. Remember, we don't even acknowledge the sodium. So what it's saying is that using H minus as a base, we're going to deprotonate next to the carbonyl. Remember not to pull off the aldehyde proton. That proton is completely non-acidic. That's not the proton you go after. You pull off the proton that's next to the carbonyl. And you could have used sodium hydride or any of a variety of other bases. It's not asking for the mechanism, but I'm showing it anyway. So hydride pulls off the proton. The electrons from the CH bond go in between the 2 carbons. and we break the carbon-oxygen pi bond. And we get the enolate. And one of the resonance forms of the enolate will have the minus charge on oxygen. That's the one we generally draw. And the other resonance form of the enolate will have the minus charge on carbon. Like that. And if you're having trouble seeing how we get from this structure to this structure, remember that drawing arrows for resonance is kind of bogus. But if you need a visual aid, then you fold those electrons in on the O minus, you break the pi bond, and you put the electrons on carbon. And that will get you to this structure. So those are the two resonance forms of the enolate. One with a minus charge on oxygen, and the other with a minus charge on carbon. Oh, and there's more. It also says circle the one that is the major contributor to the overall structure. Well, in class, we pointed out that oxygen is the more electronegative atom, so it makes more sense to put more of the minus charge on oxygen than on carbon. Still, enolates generally react at the carbon, at least in all the examples we'll ever see. Will form a bond at the carbon. But this one here is the major contributor to the overall structure. So that's all the question asked to do. General reminder about my exams: you need to do everything the question says. You don't need to do anything it doesn't say. Within reason. If the question doesn't say that you have to draw reasonable structures where carbon doesn't have 5 bonds, it doesn't need to say that. That's understood because of the class. But that's the general rule for exams. Questions on that one? Next, we need to draw a dipeptide. Whoa, that didn't work. That's better. So it's given, I'm giving the 2 side chains of the amino acids. And it says to draw first both amino acid molecules at pH 1 at pH 14. These are the 2 side chains at pH 7. So let me make a little more room. So first of all, to draw lysine, remember that by convention, we start at the nitrogen end, and at pH 1, the nitrogen will be protonated. It will be protonated at pH 7 also. Then we have the carboxylic acid carbon, which at pH 1 will also be protonated. At pH 7 and 14, this will be O- instead of OH. And then we need to get the right stereochemistry. So in this view of the amino acid, the hydrogen is on the wedge bond and the side chain is on the dot bond. And I can never remember how many CH2s in lysine. 1, 2, 3, 4, 5. One, two, three, four, 5. I did a bad job at counting CH2s today, so let me just see that again. CH2, 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 CH2. And then at pH 1, the nitrogen at the end of lysine will be protonated. At pH 14, the carboxylic acid will be deprotonated. It'll be in the carboxylate form. And at pH 14, so will both nitrogens. At pH 14, we're above the pKa of both of those nitrogens, which is going to be rounding about 9.5 or 10. Someone asked me earlier, do you have to memorize all the pKa's of all the side chains? I don't think it's really necessary. You do need to know roughly where all of the pKa's are. Maybe not exactly, but at least roughly. Certainly how those groups all appear at pH 1, pH 7, and pH 14. Certainly you will need to know that. If in order to know that you need to memorize them all, then memorize them all. But I don't think it's necessary. They're all, with one exception, they're all functional groups that we've seen before. The only exception is the guanidino group in arginine. But we've seen amines before, we've seen carboxylic acids before, we've seen alcohols, we've seen thiols, we've seen phenols. All of these are functional groups we've seen before. So I don't think it's necessary to memorize them all. Good. So that's lysine at pH 1 and pH 14. Let's do tyrosine. There is one CH2 in tyrosine. Then comes the aromatic ring. Gonna have to move that over a bit. And then comes the OH group, para to the connection. And that OH group will be protonated at pH 1. It will also be protonated at pH 7. That OH group is a pKa of around 10. And I expect you to know that because we've talked about phenols before. So at pH 14, the carboxylic acid will be deprotonated. Instead of an ammonium ion, we'll have an amine-free base. And the phenol will be deprotonated. Now, if instead of tyrosine, we had an amino acid with an aliphatic alcohol, with an alkyl type alcohol, like serine, like threonine, those OH groups will not be deprotonated at pH 14. And we can give an example later. And to draw the dipeptide, let me make sure which dipeptide. Tyrosine comes first. So to draw the dipeptide, we'll take first the tyrosine and then the lysine. And we'll form an amide. So there's our tyrosine portion. And we'll form an amide. And in this view, the hydrogen is in back and the side chain is in front. So then comes the lysine. We've got 5 CH2s. This looks absolutely dreadful, but 1, 2, 3, 4, 5 CH2s. And then comes the nitrogen on the side chain of lysine. That's going to be protonated at pH 7 because at pH 7 we're below the pKa of that amine or of the ammonium group. The ammonium group has a pKa of about 9.5 or 10. And at pH 7 we're below that. We're more acidic than that. So we're acidic enough to protonate that nitrogen. You'll notice I'm not protonating the amide nitrogen. That does not get protonated, not even at pH 1. So all we have left is the carboxylate terminal. And that's going to be CO2 minus at pH 7. It will also be CO2 minus at pH 14. At pH 1, it'll be CO2H. So let me just make sure I haven't messed anything up. Let me do a triple check and compare to what I have on the answer key, since I know that some of you are following along with the answer key right now. Oh, the answer key is wrong. I forgot the CH2 over here. Yeah, there needs to be a CH2 before the aromatic ring. That was incorrect. And since we're at pH 7, there we go. Then comes the carbonyl, then NH, then you have the lysine, and then the carboxylate group. So now that's correct. Let me save that. I'm having trouble saving that. And we'll save it as a PDF also. Good, so I'll replace that on Canvas. That was incorrect. You can see the CH2 on the side chain right here. And I forgot that in the original answer key. Okay, so much for the dipeptide. Questions on that? Next, it looks like we have some mechanism problems. In the first one, we're replacing the one and only alpha hydrogen with an iodine. And we're using acidic conditions. We've got acetic acid as the solvent. So we just need to add some lone pairs to the oxygen. And we'll draw our acetic acid molecule. That's what's going to protonate our carbonyl oxygen. Remember, we protonate the carbonyl oxygen first in acidic medium. Alkaline medium, probably first step is nucleophilic attack on the carbonyl carbon. But acidic medium, probably the first step is protonating the carbonyl oxygen. And the most acidic species we have around, it's not the strongest acid in the world, but it's the only one we've got, and it's the acetic acid. And that gives us this intermediate. And in the next step, we have to remove the alpha proton and make the enol. So reactions involving the alpha proton in acidic medium will involve an enol, and an alkaline medium will involve an enolate. I just realized there was something I forgot to say about that other problem where we were making an enolate. But we'll have to get back to that. And so the only base we have around to pull off that proton is the conjugate base of acetic acid, the acetate ion. And the reason it's okay to have a species with a minus charge in acidic solution in this case is because acetate isn't a really strong base. It's not a strongly basic anion. And it's really the only base we've got, so it'll have to do. So we pull off that proton, we move the electrons in the carbon-hydrogen bond in between the two carbon atoms, and we break the carbon-oxygen pi bond to make the enol. And there's our enol. So the next step uses the enol to attack a molecule of iodine. You'll notice we're given I2 as well. And the structure of iodine is pretty straightforward. Give or take some lone pairs. And so we first use a lone pair on oxygen to fold down in between the oxygen and the carbon and remake the carbonyl. And then we break the carbon-carbon pi bond. We have to, otherwise carbon will have 5 bonds. And we use that to form a bond between carbon and iodine and break that weak iodine-iodine bond. And that gets us this almost. Because the proton's still there. And so you get this intermediate. And then all we need to do is pull off that proton to get rid of the plus charge on oxygen. We'll again use an acetate ion in order to do that. And the O minus pulls off this proton. We break the oxygen-hydrogen bond, put the electrons back onto oxygen, and that gives us our product. Like that. So that's the mechanism of alpha halogenation in acidic medium. It can also be done in alkaline medium, but that's how it looks in acidic medium. And that's basically it for the first mechanism. Makes me want to check the answer key again. Yep. Carboxylate ion attacks the iodine, pulls off the proton. Yep, looks good. Good. So everyone okay with that mechanism? Let's now handle that second mechanism. In the second mechanism, we're treating an amide with aqueous hydroxide followed by an acid workup. This is going to be alkaline hydrolysis of that amide. And so we need to treat it with acid because at the end, you get O minus instead of OH, and you need to put the proton back on the carboxylic acid. So you need to acidify. So just like we've already said, we're an alkaline medium. I know that because I'm given aqueous base. So that's an alkaline solution. And an alkaline medium, typically we start with a nucleophilic attack on the carbonyl. Oh, drat, it won't let me do it. On the carbonyl carbon. And the only nucleophile we're given is OH minus. That's all we've got in solution is OH minus, H2O, and the amide. So OH minus will attack the carbonyl carbon. We break the carbon-oxygen pi bond. and put the electrons on the electronegative oxygen. And in your chapter 21 class notes, I gave you this in the mechanism of basic hydrolysis or alkaline hydrolysis of a nitrile. If you look carefully at that mechanism, you'll find that smack dab in the middle of the nitrile mechanism is an amide intermediate. And so if you learn the mechanism for alkaline hydrolysis of a nitrile, you automatically learn the mechanism for alkaline hydrolysis of an amide. And likewise, if you learn the mechanism for acidic hydrolysis of a nitrile, you automatically learn the mechanism for acidic hydrolysis of an amide. It's included in those mechanisms. So you don't have to learn it separately if you learn the mechanisms for nitriles. So this is going to be the intermediate that you get. In the next step, we actually have to protonate that nitrogen because we can't lose NH2 minus as a leaving group. It's not a good enough leaving group. So we'll use a water molecule in order to do that. We haven't added H3O plus yet. And it gives a rather unusual looking intermediate. You've got both a minus charge and a plus charge. The reason that this is allowed is because the ammonium group has a pKa of about 10, 9.5 or 10. And if we're in alkaline medium, we're probably at about a pH of 14. And so 14 is within 7 or 8 pKa units of the pKa of this group. So it's allowed to draw it with a plus charge. That will then make it a good leaving group because we can much more easily lose ammonia as a leaving group than NH2 minus. And so that's exactly what we will do, is lose ammonia as a leaving group. That gives, as a matter of fact, the carboxylic acid that's identically equal to our product. But we're not done yet. We're still in alkaline medium. We haven't added the H3O plus yet. Remember, when you have numbered steps like this, remember what it means. It means that we treat the amide with water and hydroxide and we wait. We wait until everything reacts that can react. And when everything's done reacting, then we add H3O plus. So we're still in alkaline medium. We haven't added H3O plus yet. That means the hydroxide ion is going to deprotonate the carboxylic acid, and we cannot prevent this from happening. So you have to show it. Nope. And that gives us the conjugate base of the carboxylic acid, the carboxylate ion. And that's what's going to be swimming around in solution quite happily until we add the H3O plus. And then the H3O plus will first neutralize all of the hydroxide, and then it will start putting the protons back on the carboxylate ion. Let's see if it'll let me do this. Yes. So the O minus picks up a proton from the hydronium ion. And then we have our carboxylic acid and can isolate it. So that's, again, alkaline hydrolysis of an amide. We do need to acidify at the end of the reaction because you don't get the carboxylic acid. The carboxylic acid gets deprotonated in the basic solution. And so to be able to isolate the neutral carboxylic acid, we need to acidify. And that's basically it. Questions on that mechanism? I think those were the only two mechanisms I put on their exam. It was a very short exam. After this, we come to the reactions part of it. The first one is treating acetic acid with butylamine in the presence of DCC. And what you need to know is that DCC reacts with a carboxylic acid and an amine, primary or secondary amine, to make an amide. Will our exam have more mechanisms than the practice exam? I can't answer that question. You should plan for it having more, just in case. It should be of a similar length to the previous exams. I think it's reasonable for 50 minutes. Good. So if you treat a carboxylic acid in a primary or secondary amine, this amine is primary. With DCC, then you get an amide. You put the N of the amine where the OH of the carboxylic acid is. And that's the product that you get. And it's butylamine, so we have 4 more carbons. 1, 2, 3, 4. So that's the product you'd get, this amide. So that's a reaction you'll need to know, the reaction of DCC with an amine and a carboxylic acid to give an amide. That's used to make small polypeptides as well. In the next reaction, we have an ester. So again, I expect that you can just look at functional groups and know what they are. We have an ester that we're reacting with lithium aluminum hydride, followed by an acid workup. And you need to know that lithium aluminum hydride reduces an ester to a primary alcohol. You're not responsible for the mechanism, though it does go by H minus attacking the carbonyl carbon. So the mechanism is not outrageous. The next one, this is an unusual question. I'm curious why I phrased it like this. This is part of an a malonic ester synthesis. And the first thing that's going to happen is that the sodium ethoxide, or rather the ethoxide ion, will pull off one of the acidic protons between the two carbonyls. So remember, NaOET is ETO minus. That's very important that you know that. And the ethoxide pulls off one of these protons. And you get the enolate. You don't have to draw all this. I'm just showing you how the reaction happens. I'll point out when we get to the final answer. But you do make the enolate. And speaking of enolates, I still haven't gone back to that other question and made my point about enolates. But there's the enolate that you get. That's the first step. In the second step, we treat it with benzyl bromide. Actually, I'll just do it like this. It's simpler. This is an SN2 reaction. The electrons come back in between the oxygen and the carbon. And then the double bond shifts out to form a new bond between this carbon and the carbon that bears the bromine. And of course, we break the carbon-bromine bond. And you get this compound. And then it says H3O plus workup. The word workup changes everything. So if you treated this with H3O plus, and especially if you heated it also, then you would hydrolyze both esters and decarboxylate. You'd get the enol, and the enol would tautomerize to the keto form. So as it is, this is the final answer. So this is the answer that was accepted for full credit. H3O plus doesn't do anything to that if it's just dilute into workup step. If it did not mention a workup, if it just said H3O plus, and did not mention a workup, then I would assume that we would hydrolyze both esters, decarboxylate that carboxylic acid, and wind up with an acetic acid derivative. So that little word workup makes all the difference. So this is the type of reaction we talked about in class today. This is the final answer on original exam. And the difference is that little word workup. If it says workup, then you don't do the hydrolysis and the decarboxylation and all that. You'll just do a very careful neutralization and isolate the diester. If it does not mention workup, then the acid will hydrolyze both esters, decarboxylate, and the enol will tautomerize to the keto form. So this is what we talked about in class today. So that's the difference between those two. So this is the answer, I hope, I'm going to check the answer key again, that I originally accepted. If it doesn't say that, it's wrong again. Yeah, not chiral, no hydrolysis or decarboxylation since no heat is given. So that's just with a very careful workup. So we're done with all these. The next question gives a nitrile, and it says we're heating it in aqueous acid. So we're doing an acidic hydrolysis of a nitrile. And that's going to give the corresponding carboxylic acid. That's a chapter 21 reaction. And that's in your class notes. So you get the carboxylic acid with the same number of carbons, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. The next one is treating an alcohol with an acid chloride. So this is alcoholysis of an acid chloride, actually in acidic solution. It doesn't really matter whether it's acidic or alkaline for these purposes because the product's the same, and you will get an ester. So that's the ester you'll get. You get the benzoate ester of this alcohol. This goes by the OH group attacking the carbonyl carbon. And we went over that mechanism in chapter 21. It's acidic alcoholysis of an acid chloride. If we had used benzoic anhydride instead of benzoyl chloride, which would look like this, you get the exact same product by the exact same mechanism. So acid anhydrides and acid chlorides have very similar reactivity. Acid chlorides are a little bit more reactive than acid chlorides, than acid anhydrides. And in the next one, this actually is a reaction from chapter 20, I think. So you recall that when you treat a nitrile with a Grignard reagent, you get a ketone. And the carbon that was the nitrile carbon becomes the ketone carbonyl carbon. And then whatever is attached to the magnesium gets attached to that same carbon. So this CH3, that CH3 right there was in the methyl magnesium iodide. That CH3 comes from this reagent. So treatment of a nitrile with a Grignard reagent or alkyl lithium for that matter, they're interchangeable, gives you a ketone. And that's pretty much it for the reactions. Questions on any of those three? I just am not trusting this answer key anymore. We fixed that. That one's right. Yes, 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 that one's right. You get the amide, you get the primary alcohol, you get the diester, carboxylic acid, benzoate ester, and methyl ketone. Good. So the final question, we used, the online homework we used in those days was called OWL. That's like active. OWL style mechanisms and active style mechanisms are the same. So they're asking for two different mechanisms to go from this alpha chloroester plus this ketone to the epoxide. And there's two plausible mechanisms. One of them goes to the enolate, and we're being asked to supply all curved arrows and all necessary inorganic species. So all of the other little small molecules are not supplied. We have to supply them ourselves. So in the first one, we're going from this compound to its enolate. And so we're going to need to pull off that indicated hydrogen. Oh, I'm sorry, it's not OH, it's OCH3. Right? Remember, NaOCH3 is CH3O minus. We don't even acknowledge the sodium. We don't write it down at all. It's just a spectator ion. We just write the anion portion. And that base will pull off this proton. The electrons from the CH bond go in between the two carbons. And we break the carbon-oxygen pi bond. That gives you this intermediate. Next, this enolate is a good nucleophile, and it looks to me like we formed a new carbon-carbon bond right there. That bond goes from that carbon to that carbon. So that means we're going to attack the carbonyl carbon using the enolate. This actually is a chapter 23 reaction. This is like an aldol condensation reaction. And without giving the structures, it wouldn't have been a terribly fair question. But with giving the structures, it's possible to solve it. So that's how that part of the mechanism looks. That gives you this intermediate. And then it looks like we've closed the epoxide by forming a new bond right there. So that means that the oxygen with the minus charge attacks the carbon with the chloride on it. Notice the chlorine is gone. It's undergone an SN2 reaction. This is a Williamson ether synthesis. We talked about that in chapter 18. And so that oxygen attacks right there. We break the carbon-chlorine bond, and we form the epoxide. So that's one possible mechanism. The other one involves a very unusual alpha elimination. These don't happen very often. And your professor may or may not have talked about carbines last term. But the way it works is our base pulls off the indicated proton, the CH bond breaks, the electrons go onto the carbon. I'm having a hard time drawing that. Can't really make the arrow quite as pretty as I would like. So the electrons go onto carbon, and we break the carbon-chlorine bond at the same time. So you get this very unusual species. This is known as a carbene. And it's a neutral electron deficient species. It's carbon with 2 bonds and a lone pair. And if you use that formula that we learned way back in chapter 1 or chapter 2 to calculate the formal charge on an atom, you'll discover this carbon is a formal charge of 0. So like I said, your professor may or may not have talked about carbines last term. Probably in chapter 8, when we talked about making cyclopropanes from alkenes. And then this carbene adds to the carbonyl. Carbenes need to do 2 things. They need to get rid of that lone pair, and they also need another electron pair from somewhere to form a bond, because it wants to have 4 bonds. And so the carbene attacks the carbonyl carbon, and the electrons between the carbon and the oxygen stay attached to the oxygen and form a bond to the formerly carbene carbon. And the carbene carbon is right here. So we form 2 new bonds. We form the carbon-carbon bond, and we form the carbon-oxygen bond. That's a way to show the mechanism in only 2 steps, as opposed to 3. Probably both happen. But it's absolutely fair game to give an active style mechanism question, even if it's a mechanism you've never seen before, because I'm supplying all the structures. And that's basically it for their exam. Like I said, that was an especially short exam that year, probably because we had to make the exams open book. That was a nightmare. No, your exams are not going to be open book. Let me go back, if I can, to this question. Where we pointed out that this after deprotonation gives the enolate. And there's your enolate ion, the 2 resonance forms. One is the minus charge on oxygen, one is the minus charge on carbon. Something I said in class today is that the base could be a lot of different things. Could be sodium hydride, that's H minus, or sodium amide. Could be NH2 minus, or LDA is another valid base. Or one thing I didn't really stress in class today is you could also use the alkoxide bases. Any of those bases are fine for deprotonating next to a carbonyl. Technically, sodium methoxide and sodium methoxide are slightly weaker bases. They are especially good for protons that are between two carbonyls, like in the acetoacetic ester synthesis and the malonic ester synthesis. But they are also valid bases. So I expect you to know all of these as bases that you might be given, which when you see them are to indicate to you that they will pull off one of the protons next to a carbonyl. Any of those bases will do. They will pull off one of those acidic protons. And we already went over the mechanism. The base pulls off the proton, the electrons go in between the carbon atoms, and we break the carbon-oxygen pi bond to give this structure. So that's something that certainly is fair game for the exam. Any of those bases will do. If you're given a ketone, aldehyde, ester, nitrile, anything with a carbonyl or carbonyl-like group that has alpha protons, any of those bases, if you're given any of those bases, it will deprotonate alpha to the carbonyl. Any of those bases will do. We've still got between 15 and 20 minutes left. Let me go. I know exactly, well, at least, well, before I say I know exactly what I'll go over, are there any other questions? Like, is there anything anyone in particular wants to see? If not, then I'll open up your chapter 21 class notes. I'm just going to pick one of these mechanisms. This is Fischer esterification over here. All of these mechanisms are kind of the same at bottom. You've probably started to notice that. Let me show you what you need to do in order to learn the mechanism. I'll just use this one. I could have picked any of the others. This doesn't mean that this mechanism is on the exam, but I am going to show you how to learn a mechanism. This mechanism reacts benzoic acid with ethanol to give ethyl benzoate. You need to be prepared to be given any carboxylic acid and any alcohol with an acid catalyst. So if you look at that document that's on Canvas called Learning and Knowing Organic Reactions, it takes you through this process step by step. And the idea is to make changes to the starting materials and write out the mechanism again. So instead of using benzoic acid, let's put a methoxy group in the power position, just because we feel like a methoxy group today. Whoops. And instead of methanol, or ethanol rather, let's use isopropanol. So that means in addition to the isopropanol, once we add an acid catalyst, you're going to have some of the conjugate acid of isopropanol, which looks like this. And we should be able to figure out what the product looks like. It should be the isopropyl ester of this carboxylic acid, which looks like this. And then what you do is, looking at the mechanism you're given, the one you're studying, be sure you're looking at a source that you can trust. Get it from the class notes. Get it from your notes from class. Get it from a source that you can trust. And write out the mechanism using these slightly altered starting materials. The first step, since we're an acidic medium, is going to be protonating that carbonyl oxygen. And we'll use the conjugate acid of isopropanol. And make sure that you copy the arrows correctly. So the lone pair from oxygen picks up a proton from the acid and puts the electrons in the OH bond back onto the oxygen to get rid of the plus charge. And as you're doing it, make sure you understand why each step happens. There's always a reason for every mechanistic step. The reason behind this one is to get rid of the plus charge on this oxygen and to put a plus charge on this oxygen to make it more electrophilic, to make the carbonyl more susceptible to electrophilic attack. And that gives you this intermediate. And then comes nucleophilic attack of the alcohol onto that very electron-poor carbon. That carbon is now so electron-poor that even a mediocre nucleophile like an alcohol is good enough to attack that carbon. So that oxygen forms a bond to carbon. Notice so far that the arrows are exactly the same as are in the original mechanism from the class notes. It's just we're using different structures. And that's how to prepare for the exam. Use different structures. Because I'm not going to give you the very same molecules. I guarantee you this mechanism, this exact mechanism as you see in the class notes will not be on the exam. I can guarantee you that. Could be a variant on that mechanism like we're doing here. But memorizing the examples from the class notes will not help you. You need to understand them and be able to go through the steps on your own without being led through. So that's the oxygen. This is the oxygen. And there's an isopropyl group attached to that oxygen. The oxygen's here. Here's a hydrogen, and that oxygen has a plus charge. And so in the next step, we get rid of the plus charge on this oxygen by pulling the proton off. And in order to do that, we use an alcohol molecule. It was ethanol in this mechanism. Here it's isopropanol. So the alcohol is the most alkaline species. Notice that if instead of OH here, I'd written O minus, that would be wrong. That would lose points. We don't have any O minus species in acidic solution. And again, we know we're in acidic solution because we're given an acidic cation. So we don't want to use any strongly alkaline species. We want to stick to neutral species and cations in our mechanism. So we get this neutral intermediate. Another very common mistake is protonating this oxygen before we deprotonate that oxygen. The reason that's wrong is because then you get an intermediate with a +2 charge. And that doesn't make sense. All of your intermediates in any mechanism, I believe, should have a charge of either -1, 0, or +1. No +2s, no -2s. I can't think of an exception. But now we protonate that other oxygen because we want to be able to lose water as a leaving group. And so we're going to use this same conjugate acid of the alcohol. Will it fit? No. So we get that intermediate. This intermediate now loses a water molecule. That's the whole point of the mechanism, is losing a molecule of water to turn a carboxylic acid into an ester. And we can use a lone pair from the OH group to help out. To help to expel the leaving group. That gives us the ester protonated. And that looks like that. And then we'll use an alcohol molecule. That's the strongest base we have in this acidic solution. We use that to pull off the proton, break the oxygen-hydrogen bond, put the electrons back onto oxygen, get rid of the plus charge. And that gives us the final product. Like that. So that's an example of using a mechanism you're given to study the mechanism by making small changes. And that's the method I recommend. I'm trying to think what I can do to help you in 4 minutes. But that illustrates the method for learning reaction mechanisms. You can apply that to any reaction you're learning. Maybe what I can do in 4 minutes is show you how to apply that method to a reaction that you don't need to know the mechanism for. Here's one. And this one again, actually, I should have used the answer key. Well, it'll probably take me just as long to draw the molecule as to open up the answer key. So here's the answer to that question. Now, the way to study a reaction like this, where you don't have to know the mechanism, is the exact same way. Let's make a small change to the carboxylic acid. Maybe instead of acetic acid, let's use butyric acid. And maybe instead of butylamine, let's use diethylamine. And we treat that with DCC. So remember our method that we used for figuring out the answer to this question. I was going to look it up in the class notes. But the method that we used says take the N in the amine and put it where the OH of the carboxylic acid is. Connect that nitrogen to the carbonyl. So copy out your carboxylic acid. And then just put that nitrogen where the oxygen of the OH was. Notice one of the hydrogens goes away. You lose H and OH. You lose a water molecule when you're doing a DCC reaction. So that would be another example of that reaction. And that's how you study reactions that you don't need to know the mechanism for. Because you're not going to be given the same one that's in the practice exam or the same one that's in the class notes. You're going to be given different molecules but be expected to apply the information you learned in class to a different situation. Applying information is an absolutely critical skill that you need to have for medical school, dental school, research in biology, any kind of engineering field, basically going on in any kind of scientific endeavor. So that's why we focus on it in this class. And that's basically it. And my cat is asleep. Good. Any last questions then? I guess not. All right, well then, I will see you in class on Wednesday when we will begin chapter 23. Chapter 23 will not be on Friday's exam. It'll be on exam number 4, but we'll begin chapter 23 on Friday. I'm sorry, on Wednesday. I will see you then.